Deviation from ideal reactors. We have been able to develop a rather simple mass conservation equation for the ideal version of the stirred tank and tubular flow reactors. When the mixing criteria of these ideal forms are not satisfied, mathematical expression for the conservation equation become more difficult. In this section, types of deviations are discussed qualitatively so that we recognize that the idealized equation presented in section 3.3 and 3.4 are not always applicable. Then in chapter 6, mathematical treatment is presented for non-ideal reactor in which isothermal homogeneous reaction occurred. In chapter 12 and 13, non-ideal behavior in heterogeneous reactor is considered. As an example of non-ideal operation, imagine a continuous flow tank reactor of poor design, inadequate mixing, such that pockets of nearly stagnant fluid exist as shown by regions marked as in figure 3.3a. The conversion will become very high in the nearly stagnant fluid, but this fluid will remain in the reactor for a long time because the volume available for flow has been reduced by the stagnant regions. The bulk of the fluid will spend less time in the reactor and hence have less time to react. The result will be an average conservation in the exit stream which is less than that of the ideal type. Figure 3.3b shows another type of deviation caused by bypassing or short circuiting of the fluid. Here a part of the fluid entering the tank follows a certain path to the exit and maintains its identity, does not mix. While doing so, again the conservation in the exit stream is reduced below that of the ideal stirred tank reactor. Well, these are extreme cases attributable to poor design. It is clear that actual reactors may deviate to some degree from ideal behavior, and the behavior of a species reactor will depend on the extent of mixing. Deviation from ideal tubular flow behavior are also possible. Two kinds of deviation are: first, some mixing in the longitudinal direction, and second, incomplete mixing in the radial direction. Figure 3.4a and b illustrates these two effects. In figure 3.3a, the inlet and exit nozzles are such that vortices and eddies produce mixing in the longitudinal direction. Figure 3.4b represents the situation where the fluid is in laminar flow forming a parabolic velocity profile across the tube. Since the molecular diffusion process is relatively slow, the annular elements of fluid flow through the reactor only slightly mix in the radial direction. Also, the fluid near the wall will have a longer residence time in the reactor than for ideal tubular flow performance, while the fluid near the center will have a shorter resistance time. The result again is a decrease in conservation. Bypassing challenging can also occur in a fixed bed fluid solid catalytic reactor as shown in figure 3.4c. The non-uniform packaging arrangement results in a higher velocity near the tube wall where the porosity is greatest. Hence, the time for reaction residence time near the wall will be less than that at a center of the tube. This means that the composition of the fluid will vary radially, so that the requirement of the complete radial mixing is not satisfied. Deviation from ideal performance divide into two classifications. The first is a flow arrangement in which elements of fluid do not mix but flow separate paths through the reactor. These elements are retained in the reactor for different times, that is, they have different residence times. The second is a flow arrangement whereby adjacent element of the fluid partially mix micro mixing. The effect of this deviation on the conservation can be evaluated provided we know the distribution of resistance time in the fluid leaving the reactor and the extent of micro mixing. Such complete information is seldom available. However, for well-defined cases of micro mixing, the effect of a distribution of resistance times on the conservation can be evaluated. Procedures for treating this factor quantitatively are considered in Chapter 6. Usually the effects are internal coils and a viscous reaction mixture. They may be large because of the great influence of temperature on the rate of reaction. Unaccounted for temperature profiles in a reactor are often more significant. If the data follows second order kinetics equation, F shows that a log plot of R versus should give a straight line with a slope of unity. Figure 2.6 shows a plot of C1 versus T. Slopes of this curve give the rate of values shown in table 2.7. Also shown in is a plot of equation F. Observe that the first 4 points establish a line with a slope close to unity as required by the second order mechanism. The last point deviates from the line just as the k value for this point obtained by the integration method was not in arrangement with the other values. The complex equation for reversible reaction can be avoided if measurements are made before much reaction has occurred. Under this condition, the concentration of the products will be small, making the reverse rate negligible. Then the data can be analyzed as though the system were irreversible to determine the forward rate constant. With this result and the equilibrium constant for an elementary reaction, the rate constant for the reverse reaction can be obtained. The initial rate approach is frequently used to simplify kinetic studies. Besides the fact that the reverse reaction is eliminated